Alright, so section 9.3, in 9.2, we did the critical value approach to hypothesis testing. In this section, we're going to use the p-value approach. I like the p-value approach because it's very similar. What you're going to see is that we're going to do a lot of the same steps we did with the critical value approach. It's just that when we get to the actual application of the criteria, that it's going to work a little differently there, because that's when we get our p-value. So let's look at our example. This was the example from last section, okay, that we used the critical value approach on. And the null is still going to be the same. The null is still 275, and the alternative is still the same, and it was not equals 275, or excuse me, less than 275. Okay, so here's our problem. We still have the null, we still have the alternative. The logic is still the same. If the null is true, that means the mean distance is approximately 275. Again, we can't expect it to be 275 because we're just dealing with samples. But if we choose the alternative, that means that we can't prove the mean is true. So if it's too much smaller than 275, then we have to go with the alternative. Again, how much smaller is too much smaller? Well, as it said in the problem, this is normally distributed, so we know the mean of the sample means is equal to the population mean, which in this case is 275, just like last time. And we know that the standard deviation of the sample means is the population standard deviation divided by the square root of the samples, which is 20 divided by the square root of 4. Let's see, where is it? Divided by the square root of 25. Excuse me, there we go. 25 samples. Lost my train of thought there. Alright, so this is 20 divided by 5, which is 4. There we go. That's where my 4 came in. Alright, so these are my mean of my sample means and my standard deviation of my sample means. So remember, we have to set up a test statistic just like we did with our critical value approach. And remember, number one, because it's normally distributed. Number two, because the standard deviation is known. We know that this is going to be a z-score, is how we're going to set up this test statistic. So just like the critical value approach, it's the sample mean minus the mean of the sample means all over the standard deviation of the sample means. So our test statistic is x bar minus 275 all over 4. Now, we solved this last time. This is part C we're in right now. Alright, so this is where the p-value part, we begin to talk about that. This is where we begin to differ just a little bit. So this is a left-tailed test because of the less than sign. Left-tailed test. So what we're going to do is we're going to compute the probability of obtaining the observed z-score, okay, that is as small or smaller than the observed value. So we want to know the probability that the test statistic that z is as small or smaller, which is less than or equal to, as small or smaller than the observed value, OV, observed value. This right here, folks, is what we call the p-value. That probability is what we call the p-value. So let's go to the next page and we'll work out the p-value part. So same problem. So refer back to your notes, and you can see the actual problem as we work through it. So what do we know about this particular problem so far? Well, remember we know that the mean is 264.4. We know that the mean of the sample means is 275. We know that the standard deviation of the sample means, we know that that is 4. We know that our test statistic is x bar minus 275 over 4. And we're trying to find our p-value, denoted by the letter P. We will always denote it by the capital letter P. So this is basically what our criteria is going to be. If the p-value is less than or equal to the significance level, if the p-value is less than or equal to the significance level, remember alpha is the significance level. If the p-value is less than or equal to the significance level, then we reject. We reject the null. Okay? Otherwise, we do not reject. Otherwise, we do not reject the null. This is our criterion for a p-value problem, okay? So the first things first, we got to find this observed value. That's what the p-value, that's what we use to get the p-value. So we've got to find the observed value. So we're going to take our x bar here, and we're going to substitute it into our formula. So 264.4 minus 275 all over 4. Now we did this in the last problem too, in the critical value approach. We just went about it a little differently. With the critical value approach, remember, we got that area, we got the z-score, and we compared z-scores. With this, we're actually just using the area to get the probability. Okay, and I'll show you more about that here in a minute. So here's our z-score. Alright. So this is the observed value. So what we're trying to do is we want to find what the p-value is. The p-value is the probability to get this observed value. What is the probability of observing that value or smaller, since it's a left-tailed test? What is the probability of observing that value or smaller? Because it's left-tailed or smaller. Okay? Well, that's where you have to know. That's where you have to know your graph here, because what we actually have here is a normal curve. So negative 2.65 is right here. So if we want to find the probability of getting negative 2.65 or smaller, we need to find this probability here, to the left of negative 2.65. Now, negative 2.65 is a z-score. How can we find the area under the standard normal curve to the left of any z-score? Well, we go back to table 2 again. Your wonderful favorite table in the back in your appendix. So go to table 2, and we're finding the value to the left, so it's going to read straight out of table 2, and figure out what that area is. Well, you figure out that that area is 0.004. So the area is 0.004. Okay? Alright, so because of that, that's the same thing as the p-value. Remember, area and probability are the same thing under the standard normal curve. So that's the same thing as the p-value. So, if the p-value is less than the significance level. Now, what was the significance level? Well, in the problem, we were told the significance level was 5%. So is 0.004 less than or equal to 0.05? That would be the significance level. Is it less than that? Well, yes, it is less. So if it's less, then we reject. So for this problem, we are going to reject our null. Reject the null. Okay? Reject the null. So this is a example of rejecting the null here. Okay, now if it had been greater, of course, we would not have rejected. If that p-value had been greater than 0.05, we would not have rejected the null. Alright, so this is how we're going to solve our p-value problems. Notice it's very similar to the critical value. I tend to like p-value. I think it may be a little easier in my opinion. I always use p-value if I'm doing a hypothesis test, but to each his own. Okay, so, well, what you need to realize is that that we need to know a little bit of terminology about this for it to make a little sense to you. So, here's our p-value terminology. Alright, so the p-value is the probability of getting sample data at least as consistent with the null as the sample data actually obtained. The p-value, we use the letter P to denote it. Alright, so here's the criteria, which I've already pointed out for you. Okay. If the p-value is less than the significance level, then we reject. Otherwise, we do not reject. That's the criterion for these p-value problems. If the p-value is less than or equal to the specified significance level, we reject. That's for all p-value problems, okay? So keep that in mind. Not just the left-tailed. It happened to be left-tailed this time, but for all of them. Alright, so for instance, if I tell you that a significance level is 10% and we get a p-value of 0.07, well, the p-value is less than or equal to the significance level, so we would reject. Okay, the p-value is less than or equal the significance level. Now if that significance level was 5%, the p-value would be greater than the significance level, so we would not reject. So this is a reject, not reject. Okay, so that's kind of the difference between them. In fact, here's what we can say. The p-value of a hypothesis test equals the smallest level at which the null can be, the smallest significance level at which the null can be rejected. That is the smallest significant level for which the observed data results in the rejection. I would commit that to memory. Just kind of memorize that. There's some concept questions on homework that will appear with that. Alright, so determining the p-value for a one mean z-test. Alright, so a little bit of meaning first. If you look at this picture, you're going to see something called z sub 0. Do not think that z sub 0. This is just a way of denoting the observed value. Okay, the observed value. So our observed value was negative 2.65 in the last problem. That's what this is talking about. Now, if it's a two-tailed test, We get this by taking the absolute value, or the magnitude, of these areas. Now, the probability here and the probability here together give you your p-value. Not just one of them, both of them together give you your p-value. Alright, so with a left-tailed test, this is the one we just did, the p-value is here. It's the area to the left of the observed value. On a right-tailed test, it's going to be the area to the right. So let's look at some examples. For instance, the value of the test statistic. So they've given you the z-score here is negative 1.19. They want you to determine the p-value. Now, how do we determine p-value again? We take our z-score and we go to table 2 and we look up the area. And that area is our probability of our p-value. That is our probability. And so if you go to the back of the book, you will find that negative 1.19, that the area is 0.1170. So the p-value is 0.1170. Alright, letter B. At the 5% significance level, does the data provide significant evidence to reject the null in favor of the alternative? Well, remember, this is how we reject. P has to be less than or equal to the significance level to reject. So the significance level is 0.05, but the p-value is 0.1170. So it's greater than the significance level. So we do not reject. We do not reject the null. So basically what we're saying here is at the 5% significant level, the data does not provide sufficient evidence to reject the null. Okay, it does not provide significant evidence to reject the null. All right, let's try another one. All right, now that last one, that was a left-tailed test. Just I didn't bring that up in the beginning, and that's my fault. That's why you were able to read straight from table 2, because it was a left-tailed test. So you were able to go to table 2 and look up the z-score and get the area just like we did, because it was left-tailed. Now this next one is right-tailed. So think about what that's telling us here. If you have a right-tailed test, 2.85. So that means 2.85, and we're looking at the area to the right. Okay? So, we can still go back to table 2, and let's do that together. Go back to table 2 and look up 2.85. Okay? I'm going to do that with you. So get your book and go back to table 2. If you don't have your book, make sure you go get it. Pause the video and go get it. 2.85, if we look up 2.85, that's going to be 0.9978. Excuse me. 0.9978. Now, 0.9978, though, 0.9978 is obviously all of this area here. This is 0.9978. We're trying to find this area to the right, not the area to the left, because remember, table 2 is based on the area to the left. So remember, the whole area underneath the normal curve is 1. So we have to subtract 0.9978 from 1. And when you do that, you get 0.0022. This is the area to the right here that we're looking for. So our p-value is 0.0022. At the 1% significance level, does the data provide sufficient evidence to reject the null? Well, remember, in order to reject, we're looking at this. So this is 0.01 would be our alpha, 0.0022. So yes, it does provide sufficient evidence because it's less than our significance level. So yes, it does provide sufficient evidence to reject the null. Alright, so let's look at another example. The two-tailed test. The two-tailed test. And they tell you, they only give you one of the two tails here. They tell you z is negative 1.71. But because it's a two-tailed test, they're expecting you to know that based on past experience, this z-score is the negative 1.71, but because it's two-tailed, we have this one over here, and it's positive 1.71. That's what they're expecting you to know there, okay? They're expecting you to kind of have that down by now. But remember, the p-value is going to be both these areas, okay? That's going to be the p-value. Both areas. So these are symmetrical. So because it's a normal distribution, so what we have here is we only really need to solve one of these areas, and I'll show you why. So since we read the table from the left, since we read table 2 from the left, I'm going to solve the one that they give us, negative 1.71, because that's the area to the left. Okay, so go to table 2, find negative 1.71, and figure out what the area is. The area to the left of negative 1.71 is going to be 0.0436. 0.0436. And if you flip to the back, you can confirm that. Negative 1.71, 0.0436. Now that's just this area here. We have to include this other area. So to get the p-value, since these are symmetrical areas, all we have to do is multiply by 2. So multiply by 2, and that will give you both areas. 0.0872 is our p-value. So notice our significance level is 5%. So 0.0872, 5%. Okay? Well, this is greater than 5%. This is greater than 5%. So, because it's not less than or equal to, then it does not provide sufficient evidence to reject the null. It does not provide sufficient evidence to reject the null. So hopefully you're kind of getting the feel for these p-values. So here's our approaches for the p-value testing. State the null and alternative. Decide on the significant level. That's typically given to you. Okay. Compute the value of the test statistic, our z-score. Use it to determine the p-value. And if p is less than or equal to alpha, reject the null. Otherwise, do not reject it. And then interpret your results. Alright, so using the p-value to assess evidence against the null. Many researchers don't even look at the significance levels, don't even refer to the significance levels anymore. They just use the p-value to assess strength against the null. So here's what they're looking at. If the p-value is greater than 0.1, they say it's weak evidence against the null or no evidence against the null. If it's between 5% and 10%, it's moderate. Between 1% and 5% is strong, but less than 1% is considered very strong evidence against the null. So what we generally say is small p-values provide evidence against the null. Larger p-values do not. Okay? Hopefully this made sense to you. If you have any questions, please feel free to ask your instructor.